Hello everyone, we are looking at question 47 of GATE 2014 chemical engineering paper, and the question is: the bottom face of a horizontal slab of thickness 6 mm is maintained at 300 degrees Celsius. The top face is exposed to a flowing gas at 30 degrees Celsius. The thermal conductivity of the slab is 1.5 watt per meter per Kelvin, and the convective heat transfer coefficient is 30 watt per meter square Kelvin. At the steady state, the temperature at the top face we have to find. So let's draw a general schematic. So we have been given a horizontal slab, and the thickness we have been given as 6 mm, that is 6 into 10 raised to minus 3 meter. And the bottom face of the slab is maintained at 300 degrees Celsius. So this is 300 degrees Celsius, and the top face is exposed to a flowing gas of 30 degrees Celsius. So let's just consider we have a flowing gas over here, and its temperature is 30 degrees Celsius. The thermal conductivity of the slab, that is K, is 1.5 watt per meter Kelvin, and the convective heat transfer coefficient, the H over here, is 30 watt per meter square Kelvin. At steady state, the temperature of the top face, so we have to find the temperature at this, so let's just call it as temperature at surface, that is Ts. So here initially we have been given the temperature as 300 degrees Celsius, and then we will be having conduction resistance over here, conduction R, that is R1, and then over the surface we will be having convective resistance, that is R2, and ultimately the temperature over here is 30 degrees Celsius, and over here we are having Ts, that is the temperature of surface. So we can write the energy balance as Q of conduction is equal to Q of convection. So where Q of conduction will be delta T for this conduction upon R1 we are calling it as resistance, so for this conduction it will be delta X upon Ka, and for convection R2 will be 1 upon Ha, so that is R1, and for convection delta T upon R2. Now for this conduction the temperature difference will be 300 minus Ts, that is 300 minus Ts upon delta X upon Ka. So heat is being transferred in this direction, so the thickness through which it will transfer is this 6 into 10 raised to minus 3 mm, so that is delta X is 6 into 10 raised to minus 3, and into K is the thermal conductivity, upon into area. So over this area the conduction will occur, and also this is the same surface area through which convection will also occur. So for convection the temperature difference will be Ts minus 30 upon 1 upon Ha. So the value of H and the area will be here, so this area will get cancelled out, and we can replace the value of K as 1.5, so this will become 1.5 into 10 raised to 3 upon 6 into 300 minus Ts upon is equal to Ts minus 30 into value of H, we have been given it as 30. So this we can simplify as, so this will get cancelled out, and we will be having 150 into 300 minus Ts is equal to 6 is 18 into Ts minus 30. So this will become 45,000 minus 150 Ts is equal to 18 Ts minus of 540. So you can solve this equation and you will be getting the temperature of the surface as 271 degrees Celsius. So we will report our final answer as 271 degrees Celsius.